general relativity step by step. I calculated in the last one this metric tensor here for a Cartesian system, which is dead easy. So what I'm going to do now is to consider it in the h theta system. So let's just have a think about that. Let's just define a point here, which is point P. Actually, I'll pinch in a bit, makes my writing look a bit better. This is point P, which is h and theta, that's point P, and here's a point P dash, which is h plus delta h, and of course theta plus delta theta. So I need to work out that distance squared. So d squared equals what? Well, point P in Cartesian system is just x comma y, which is h and h tan theta. P dash is just h plus delta h. Oh no, it's not a vector. Comma h plus delta h tan theta plus delta theta. Tan of theta plus delta theta. Okay, so that's the new x, and this is the new y. Representing the fact that we have moved from here, we've changed in the x direction by that much, and we've changed in the y direction by something altogether more complicated. But now we use the fact that I'm going to neglect second order terms. Which makes my life a lot easier. So what's P dash? P dash is now h plus delta h, comma, I'm just going to expand this and I'm going to ignore terms of the second order. So what have we got? We've got h tan theta plus delta h tan theta plus h, differential of tan is sec squared theta. Actually, it's not a d, it's a delta. No, I've got that right. Plus higher order terms. I mean, yeah, we've got a delta h and a delta theta that come together, but we'll see we don't need that. So delta x is equal to delta h because we started at h and then we've gone to h plus delta h. Delta y is just, well, we started at h tan theta, there it is, and what we've moved, this thing here is the delta y. So delta y is, let's just write it out, delta h tan theta plus h sec squared theta delta theta. And my distance is just delta x squared plus delta y squared, just by boring old Pythagoras. Delta y delta x, and there's d squared. Equals what? Delta h squared plus delta y squared. So it's delta h tan theta plus h sec squared theta delta theta all squared. See again how I'm not scared to write it out. Delta h squared plus delta h squared tan squared theta plus h squared sec to the 4 theta delta theta squared, that term squared, plus the cross terms, 2 delta h tan theta times h sec squared theta delta theta, just times delta theta. Let me just coalesce my terms here. We've got delta h squared times 1 plus tan squared of theta plus delta theta squared times this thing here, h squared sec to the 4 theta plus the cross term delta h delta theta, which is this term, which is this term here, that one and that one, times 2, what have I got? H tan theta sec squared theta, which is a bit of a mess there. Bit of a mess. Okay. Oh, there it is. Now what I'm going to do, that's my ds squared, which is my distance squared. Distance squared equals this thing here. So what I'm going to do is to rewrite it in a slightly cheeky notation. I'm going to write it in the form of a quadratic form. Delta theta times, I'm going to give myself a bit more space. I'm going to give myself a bit more space. I'm going to write it down here. Delta H, delta theta, a matrix and a row vector here. I'm abusing notation. I don't want any purist, super rigorous people phoning me up and saying, look, Ankin, you've got it all wrong because it's not a matrix. I know it's not a matrix. This is just a way of me keeping terms together. We've got a sec squared theta here because it's that term there. 1 plus tan squared equals sec squared. This isn't going to be big enough, is it? This isn't going to be big enough. I'm going to have to rewrite it again. Let's make it out there. Delta H, delta theta. This term here is this term here, which is h squared sec to the 4 theta. And we've got 2 off-diagonal terms here, which I'm going to split equally. I don't absolutely have to do that, but it's conventional to require that your fundamental tensor is, sorry, your metric tensor is symmetric. What have we got here? We've got 2, and we've got 2 terms, so that's cool. H tan theta sec squared theta, and here's the same thing, tan theta sec squared theta. So this thing here is my Gij, and I'm going to write it out again. I'm just going to play with it. We've got sec squared theta, h tan theta sec squared theta. Same thing here, tan theta sec squared theta, h squared sec to the 4 theta. That's my h row there. This is my that's the column there, h and theta. So I can write that as GHH, and I can just read it off. GH theta equals G theta H equals H tan theta sec squared theta, G theta theta, which is the lower right term, equals H squared sec to the 4 theta. There it is. This is the metric tensor. I should put tensor in brackets because I've not really defined a tensor yet, for the H theta coordinate system. Beautiful. There it is. And as I say, I've ordered it in a matrix because it makes this quadratic form quite nice and easy to visualize, but it's not really a matrix. I'm going to stop there.